A very good afternoon to everyone present here. I, Amina Sheikh, on behalf of the Applied Mechanics Department, LD College of Engineering, Ahmedabad. Welcome you once again for the last session of this faculty development program on advances on earthquake safe design and construction conducted under AICTE Training and Learning Academy. It gives me immense pleasure to invite our next speaker, Dr. D.P. Soni, who is currently a professor and head of the Department of Civil Engineering with specialization in civil structural engineering at Sardar Vallabhbhai Patel Institute of Technology, Vasar. Sir completed his bachelor in civil engineering from Government Engineering College, Modasa in 1995. Sir has completed his master in structural engineering from DTIT Nadiad in 2000 and PhD in earthquake engineering from DTU Nadiad in 2010. Sir has more than 25 years of experience in this field. Sir has been published around 16 national and international journals, and Sir has also been a part of 27 national and international conferences. Sir is also a life member of Indian Society of Technical Education. Now, I would like to request Dr. Soni sir to share his wonderful experience and words of wisdom with us on the concept of seismic-based isolation, effectiveness, analysis, and design. Now, over to you, sir.
Thank you for your kind words. I would like to extend my thanks to Applied Mechanics Department for giving me an opportunity to interact with you in this faculty development program. So let me to share my screen. Is my screen visible?
Yes, sir.
Okay.
Yes, sir, it is visible.
Okay. Okay. So the topic of our today's discussion is seismic base isolation, its effectiveness, analysis, and design. The scope of the discussion would be restricted to the four main points. Number one is to present the concept of base isolation, then to study why and under what conditions the isolation is effective in reducing the seismic forces. Next is how to do analysis of base isolated structure. And the fourth last one is the design of base isolated structure. So essentially, the presentation is divided into four parts. Part one deals with the concept of base isolation. Second part deals with why and under what condition isolation is effective. Third part will be discussing about the analysis of base isolated structure. And in the last part, we will be discussing about the design of base isolated structure. So this is the overview of today's discussion on seismic isolation system. So starting with the first part, concept of base isolation. Many of you might be aware with the concept of base isolation. However, we will quickly review the concept of base isolation. So as you know, in base isolated structure, there is a flexible layer which is introduced between the superstructure and the foundation. And because of this flexible layer called base isolator, the fundamental period of the building increases, and thereby the lateral forces acting on the system reduces. So this is the overall principle of seismic base isolation. So essentially, it is a technique of decoupling the building from the ground to reduce the earthquake motion to be transferred to the building. In a base isolated building, flexible devices called isolators are introduced between the building and the foundation. So the base isolation basically results in elongation of period of the total system. And second, addition of damping in this system. So as we discussed that because of the flexibility of isolation layer, the fundamental period increases. In addition to this, the isolation system, it has its inherent damping, and this damping helps in reducing the seismic response. So the base isolation works on twofold. One is period elongation and the second is addition of damping in this system. So let us see how the period elongation system works. So here we can see a typical response spectra as per IS 1893, and you are familiar with this. On y-axis, spectral acceleration normalized by the gravitational acceleration is plotted, and on x-axis we have time period of the system. Then the graph is given for three type of soil: type 1, type 2, and type 3. Now suppose we have one base isolated building. Just for our simplicity, let us assume that we have single storied fixed base building, right? And suppose I am assuming that the time period of the fixed base building is, let us say, 0.5 second, right? Now, if the same building is kept on isolator like this, same building, same column size, beam size, I mean, same stiffness, same mass, everything is same, but it is kept on isolator, okay? So upon putting isolation system, we know the time period will increase due to the flexibility of isolation layer. Here I am supposing that after putting the system on base isolation system, let us say the time period increases to 3.5 seconds. Okay. So that time period will be denoted as TB, time period of the base isolated system. So here 3.5 second time period is so. Now let us examine the spectral acceleration. See, for fixed base system, the spectral acceleration SA by G value, we can see it is 2.5 times the gravitational acceleration. However, that for the base isolated building, the spectral acceleration comes out to be SA by G value is equal to 0.33 times G. Now we know that the base shear or the total earthquake force is directly proportional to the spectral acceleration. We can see that there is a drastic reduction in spectral acceleration. See, it has reduced to 0.33 times gravitational acceleration from 2.5 g. So the lateral force or the seismic force will reduce drastically, and thereby, isolation system works and isolation system reduces the structural response. Just for interest, it is important to know the ratio. See, the ratio, I mean 0.33 divided by 2.5. The spectral acceleration of base isolated system divided by the spectral acceleration of a fixed base system comes out to be 0.33. That means, just for example, if we consider that the total earthquake force is suppose 100 kilonewton on fixed base building. Now, if the same building is mounted on base isolator, then the earthquake force will reduce to 0.13 into 100, that is 13 kilonewton. Okay, so that is a drastic reduction in total horizontal force, and this is only because of the period elongation. So period elongation plays major role in reducing the structural response. Now, the second part is, second fold is addition of damping. Effectiveness of base isolation is because of two reasons. One reason is period elongation that we discussed, and the second reason is addition of damping in the system. So when the system is kept on isolator, it has inherent damping. If it is rubber bearing, see, it can be high damping rubber bearing, or even it can be friction pendulum system or any other sliding isolation system. So whether it is a sliding system or a rubber system, both have their own damping, right? And to explain the influence of damping, we have plotted two graphs: one spectral acceleration versus time period, and the second one is spectral displacement versus the time period. The graphs are plotted for different values of damping, say 5%, 10%, 20%, and 30%. So here we can see from this graph that as the damping increases from 5, 10, 30, as we move down, the spectral acceleration value decreases. Okay, And when the spectral acceleration values are decreased, the total horizontal force or base shear or earthquake force, they all reduces. Okay. Similarly, the damping also useful in reducing the spectral acceleration as well. So we can see that as the damping increases, on y-axis we have plotted the spectral displacement. So upon increasing the damping, spectral displacement also reduces. Okay. So these are the two main reasons for the effectiveness of the base isolation. Okay, that is period elongation, and the second one is addition of damping. Uh, Many of us might have seen this figure. Okay, it's a well-known figure that explains the behavior of base isolated building. On left side we have fixed base building, and on right hand side we have base isolated building. On the left side building, fixed base building, we can see significant inter-story drift, whereas on right hand side the superstructure essentially behaves as a rigid body. Okay, so there is a very small inter-story drift. So in fixed base building, the behavior is like cantilever type. And in the base isolated building, the behavior is like a rigid body. Okay. So it is because of the presence of flexible layer, the displacement is mainly concentrated over here. Okay. In base isolated building, the displacement is concentrated at the isolation level. And hence the fundamental mode of vibration changes from cantilever to a rigid superstructure. So this animation is helpful for understanding the basic concept of base isolation system. Moving next, uh, the effect of base isolation. See, as we have seen previously, that it reduces the floor acceleration and interstory drift. Then there is a less or no damage to the structural members. And the next one is better protection of secondary system. Okay. So these are the three main effects of base isolation system, which is further explained by these two diagrams. Okay, over here we can see that the displacement, or say it is the seismic forces, follows the triangular pattern. Means the forces are more at the top, and as we go down, the forces are reducing. Okay. Whereas in base isolated building, we can see the uniform displacement at all the floor because of the rigid body behavior of the system when it is mounted on the base isolation system. So building with fixed base experiences higher story drift and higher amplitude during the earthquake, which we can see over here. Whereas building with base isolator experiences lower story drift and lower amplitudes. So these are the effects of base isolation. Next, advantages of base isolation. Okay, see, the base isolation makes building more functional at design basis earthquake level and less damageable at maximum considered earthquake. You know, DBE it has 5% probability of occurrence, and MCE it has 2% probability of occurrence. Then, from safety point of view, the building becomes more robust against earthquake. So this is the another advantage. And the last important, base isolation is most reliable and widely adopted concept among all other passive devices. So these are the three main advantages apart from other several advantages of base isolation system. Now, moving to the types of base isolation system. See, there are many types of base isolation system have been developed, designed, and implemented in practice. All the isolation system can be grouped into three categories. One is rubber isolation system, second is rolling type isolation system, and the third most advanced is the sliding type isolation system. So let us have a quick overview of the three type of isolation system. The first one, rubber type isolation system, it is called elastomeric bearing. Then second one is rolling bearing, and the third one is sliding bearing, which works on the principle of sliding. Now, elastomeric bearing. Elastomeric bearing can be of two types. See, here I have tried to classify the different type of isolation system to have better picture, to have better overview of the base isolation system. So elastomeric bearing can be steel reinforced isolator, or it can be fiber reinforced isolator. Okay. So the example of steel reinforced isolator is the laminated rubber bearing. Then lead rubber bearing. Lead rubber bearing is also called NZ system. because it was developed in New Zealand. And the third type is high damping rubber bearing. Okay, so these are the most common type or most early isolation system. Then we have fiber reinforced isolator. Depending upon their shape, it can be rectangular or circular. There are fiber reinforced provided inside the rubber. So this is regarding the elastomeric type bearing. Now here a typical two elastomeric type isolation bearing is shown with their cross section. So on the left hand side, we have laminated rubber bearing, in which we can see that there is a alternating layer of steel and rubber. This black color portion is a steel plate. This is a steel plate, and white color portion is a rubber. So there is alternate layer of rubber and steel sandwiched between two steel plates called top cover plates and bottom cover plates. So the basic components of the laminated rubber bearings are steel and rubber plates built in alternating layers. This bearing exhibit high damping capacity. It has horizontal flexibility and high vertical stiffness. So high vertical stiffness is imparted because of the presence of alternating steel plates. And due to rubber, it gives horizontal flexibility as well as it gives damping characteristics. So this is the cross-sectional view of a typical laminated type rubber bearing. Then on the right hand side, there is improved version of laminated rubber bearing. See, everything is the same, but at the center, a lead core is inserted. See, this is called lead core. And the lead core, the function of lead core is to dissipate energy coming due to the earthquake. Okay. So it has additional energy dissipation component. Therefore, its performance is superior over the laminated rubber bearing. So here, the energy dissipation core, or called lead core, it reduces earthquake forces and displacement by energy dissipation, and it also provides resistance to wind. Then steel plates provide vertical load carrying capacity, uh, and it confines the lead core as well. And at last, the internal rubber layer, they provides the lateral flexibility. And this system is sandwiched between the bottom mounting plate and the top mounting plate. So this is regarding a typical first kind of isolation system called rubber type isolation system. Now, second one, rolling bearing system. So different type of rolling bearing system have been developed. Only few of them have got place in actual practice. However, other systems still remains in literature. So the first type is double concave rolling ball bearing system, then circular or elliptical rolling rods, then ball system with restoring properties, then mushroom shape basements, then base isolation with spring and calm system, then sloped rolling type bearing, then ball in cone bearing system, then eccentric rolling isolation system, then non-concentric rolling isolation system, and last, the rolling ball isolation system. Okay, all of this system, they work on the principle of rolling. See, the general configuration is something like this. There will be one plate at the top and one plate at the bottom, and then spherical balls are inserted in between. Okay. So this is the general construction of rolling bearing system. We will discuss one of them here. See, ball type with restoring property. So you can see that there is one top plate and one bottom plate, and there are two concave shape portions, and a rolling ball is inserted in between. Okay, so concave shape is provided to have restoring force capacity, and this ball rolls within the concave shape. Now, the main disadvantage of this type of system is the spherical ball, it has point contact with the surface, rolling surface. And because of that, there is a high concentration of stresses in some particular region. So this is one of the disadvantage of rolling type system. So as we have discussed over here, that balls are put inside two concave spaces between structure and foundation. And the obvious defect in this kind of technique is that the high stresses are produced in the contact area. However, the ball type isolation system is used in protecting the special equipments, right? Okay. Now the third type, sliding bearing, the advanced version of seismic isolation, it is the sliding bearing, and it works on the sliding principle. Here we have categorized the sliding system into three groups: single sliding surface, then sliding isolation system with double sliding surface, and the isolation system with more than two sliding surfaces called multiple sliding surface. See, it is very interesting to see different types of single sliding surface. The one is friction pendulum system. Okay, many of us might have seen the friction pendulum system. It has one concave surface and there is one slider which slides on the concave surface. Then variable frequency isolator, variable curvature friction pendulum system. Both of this, they are similar to the friction pendulum system, but the sliding geometry is different. In friction pendulum system, the sliding geometry is described by circle, right? Whereas in variable frequency isolator and variable curvature friction pendulum system, the sliding geometry is non-spherical. It is described by some other mathematical function. Okay. Otherwise, all the things are same. Then the next one is sliding concave foundation. Here the foundation is given a special kind of concave shape and isolation property can be achieved. Then double wedge base isolation device, where double surfaces are used. Of course, double word is used, but the sliding surface is only one. Then polynomial friction pendulum isolator. It is also similar to this friction pendulum, but the sliding geometry is described by the polynomial mathematical function. Then variable friction pendulum system. So variable friction pendulum system is again same as this friction pendulum system, but the thing is, in all friction pendulum system, variable frequency, all above, the friction coefficient mu is constant. Whereas in variable friction pendulum system, the coefficient of friction mu varies along the displacement. So mu becomes the function of isolator displacement x. Okay, other things are same. And the last one is pure friction system. And pure friction system, we know it has no restoring force capacity. Right? The best example is a sand layer, normally used in a single storied building between the superstructure and foundation. Okay. However, it has no restoring force. So these are the examples of single sliding surface base isolation system. Then the improvement to single sliding surface, that is called double friction pendulum bearing without articulation, then uplift restraining friction pendulum system. So in double friction pendulum system, okay, in the next slide, the figure is shown, but just for our understanding, there is one slider which is sandwiched between the top sliding surface and bottom sliding surface. That is called double friction pendulum system. The next one is uplift restraining friction pendulum system. It is more or less similar to this, but there are two concave surfaces and in the form of rail, and they are provided orthogonally like this, top and bottom. So that is the example of double sliding surface. And then the last one is multiple sliding surface, where we have triple friction pendulum system, quintuple friction pendulum system. This QTFP is the latest advancement in seismic base isolation sliding type technology. So we will have again, many of us have seen this figure. This figure is presented just to show the size of friction pendulum bearing. So a man is standing at the center. So with respect to the height of a man, we can visualize the size of the bearing as well as the size of the articulated slider. And then on the right hand side, the operation of friction pendulum bearing is shown. Now, this figure shows the cross section of double bearing, double concave friction pendulum system, then triple friction pendulum system, TFPS, and uh, quintuple friction pendulum system. Moreover, on the left side, another special kind of sliding bearing system is shown, that is called RFBI. RFBI, Resilient Friction Based Isolation System. So this system is basically a combination of NZ type system and FPS system, because it has component of NZ as well as FPS system. So how it differs from NZ type system, you will see there are top connecting plate, right? Bottom connecting plate. So here we have three components. Okay, the top and bottom connecting plate, they also slide over each other. So there is a friction component mu. Then you will see one central lead core. So it has one hysteretic component Z, and the another, there is alternating layer of steel and rubber. Okay, so that gives you the horizontal flexibility. So we have damping component. So see the bottom connecting plate, then sliding rings, then central rubber core, then peripheral rubber core, bottom cover plate, etc. So in RFBI, it composed of a set of flat rings which can slide on each other with central rubber core and peripheral rubber cores. And it combines the beneficial effects from friction damping with that of resiliency of rubber. So it is same like this. So it's a combination of NZ type system and friction pendulum system. So this is regarding RFBI, a special kind of sliding isolation system. Now on the right hand side, we have double concave friction pendulum system. It is called DCFP. And we can see there are two sliding surface number 1 and sliding surface number 2. And there is an articulated slider which is sandwiched between the two plates. Now, the advantage of this system over single sliding friction pendulum system is that we have more parameters. So in single sliding surface, we have only two parameters, that is coefficient of friction mu and radius of curvature r. Whereas here we have four parameters, that is radius of curvature of top surface, radius of curvature of bottom surface r2, friction coefficient of top surface mu1, and friction coefficient of bottom surface mu2. We have four parameters. So we can have better control over the seismic behavior of this structure. So DCFP is the improved version of a single friction pendulum system. Later we will see that this particular isolation system is used in one of the building constructed in India. Then the next type is triple friction pendulum isolation, TFPS. In TFPS, we can see four sliding surfaces, number 1, 2, 3, and 4. So we have four radius of curvature and four coefficient of friction. But usually the property of second and third sliding surface is kept constant. Property means the radius of curvature r3 and coefficient of friction mu3. Similarly here, the radius of curvature r2 and coefficient of friction mu2. Means r3 and r2, they are kept equal. Mu3 and mu2 both are kept same. So we can represent double sliding surface with similar properties by an equivalent single sliding surface. Okay, we can mathematically model like this. So if the radius of curvature and coefficient of friction of two surfaces are same, then they can be modeled using a single surface. So essentially now we have how many surfaces? Number 1, then number 2, which is the equivalent surface, and number 3 is this. So essentially we have three surfaces. Therefore, it is called triple friction pendulum system in spite of having four sliding surfaces. So this is again improved version of double friction pendulum system, and the latest version of multiple sliding surface is QTFP, that is called quintuple friction pendulum system, in which we can see six surfaces, 1, 2, 3, 4, 5, and 6. And again, the properties of third and fourth system is kept same. Means R4, R3, mu4, mu3, they are kept same, so that they can be modeled by a single sliding surface. And finally, we have five surfaces like number 1, number 2. Here it is 3, 4, and 5. Therefore, it is called QTFP, quintuple friction pendulum system. So this is regarding the multiple sliding isolation system. Now, having understood the different type of isolation system, its classification and its salient feature, it is essential to understand the dynamics of base isolated building. Here, the dynamics is explained with the example of single-storied building, and then the concept will be extended to multi-storied building as well. So here, a single-storied building on left-hand side is shown. The mass is M, stiffness is K, and damping is C. The same single-storied building is now kept on isolation system, base isolation system. The base isolation system considered here is rubber bearing, and it has been shown by several researchers that the rubber bearing can be modeled as a linear isolation system whose force deformation behavior is linear. So we have used here the linear behavior of force displacement relationship for the isolation system under consideration. And because of this linearity, a well-known response spectrum method of analysis is used to have insight into the dynamics of base isolated structure. See, most of the isolation system are nonlinear, and therefore we have to carry out the nonlinear dynamic analysis. However, since our assumption, the assumed relationship of force versus displacement is linear for the particular rubber isolation system, we can use it to have insight into the behavior of the system. So same mass is kept on the top, same stiffness K and C. And of course, when the system is kept on base isolation system, one must have a base mass. The base mass is taken as MB. Now the isolation system is described by its stiffness called isolator stiffness KB. Okay. And its damping is CB. So B subscripts is given to identify that it is related to the base of the building. Now suppose the fixed base period TF of this system is, let us say, 0.4 second, and the damping is equal to, assuming 2%. Now this system, when kept on isolation system, we know that its fundamental period will increase. Okay, so suppose the increase in time period is 2 seconds, that is called TB, means isolation period. Then we have assumed here that the base mass is equal to 2/3 of the base mass. It can be anything. It can be 2/3 of the base mass, or sometime MB is equal to M. That all depends upon the design. But here, for explanation purpose, we have assumed that the base mass is equal to 2/3 of the mass of the slab. Then the rubber has its own damping, and that damping is considered as 10% of the criticals. So for the purpose of comparison, we have taken the same building, a fixed base building and the base isolated building. Now, the isolator stiffness, let us have an insight on the the dynamics of the base isolation system. The isolator stiffness, let us first of calculate. KB is equal to M into omega square. The simple equation is used. This first part represents the total mass, M, and the second part represents the omega, M into omega square. Omega is equal to 2 pi upon TB. So upon putting values, TB isolation period 2 seconds, we get 16.45 into M. It is expressed in terms of mass of the floor. Then the stiffness of one-storied building, that is fixed base building, same equation is used. K is equal to M omega square, but here fixed base time period TF is used. Okay, so TF is equal to 0.4 second, and the stiffness is coming to 46.74 M multiplied by the mass. So the first stiffness is the stiffness of isolation system, and the second one is the stiffness of the fixed base building. Now we can see that the stiffness of building is very high compared to the base isolated. It is because of the flexibility of isolation system. Okay, upon introducing the flexible layer between the foundation and superstructure, the system becomes flexible. In other words, its stiffness reduces. So we can say there is a huge reduction in this stiffness. and the reduction in stiffness will then become responsible for reducing the overall structural response. Next, the calculation of damping constant of the fixed base building. Again, we have used the most common equation, C is equal to 2 xi m into omega. Okay, where omega is equal to 2 pi upon Tf. So damping is coming 0.628 times the mass, and the damping of the base isolated building, same equation, C is equal to 2 xi m into omega, but omega is taken for the base isolated building. So upon putting value, we have 1.047. Okay, we can further compare these two value. Since the isolation system, it has its own damping, so we can see the damping coefficient of base isolated system is high as compared to the fixed base building. So this damping will also reduce the structural responses, as we have seen in previous slides. Okay. Now moving towards, once we obtain this property, we can go for the eigenvalue analysis. To do the eigenvalue of analysis, we know that we need mass matrix and stiffness matrix, and it is very easy to construct the mass and stiffness matrix. So as a part of the response of base isolated building using RSA, we have constructed the mass matrix and then the stiffness matrix. Okay, one thing I would like to highlight is, see, this is our fixed base structure and this is our base isolated structure. See, it's a single storied building, therefore degrees of freedom of single storied building is 1 only. Okay. Now when the same system is kept on isolation system, the degrees of freedom will increase by 1. One more degrees of freedom is there at the isolation level. Okay. So suppose if there is a n degrees of freedom of a multi-storied building, then the degrees of freedom of base isolated building would be n plus 1. Okay. So for single storied building, the mass matrix is of size 1 by 1. Become 2 by 2, which you can see here. Okay, mass matrix is of size 2 by 2 and the stiffness matrix is of size 2 by 2. Okay, the first element is MB, means our numbering system is like this. This is DOF number 1 and this is DOF number 2. So stiffness matrix, K1 plus K2, then K2 minus K1, like we can construct the matrix. So mass matrix is this, stiffness matrix, both have 2 by 2 size. And damping matrix can be constructed in a similar way, CB plus C minus C and C. Okay. Say this particular example becomes the case of non-classical damping. Okay. Those who have undergone the course on structural dynamics, they must be knowing the classical damping and non-classical damping. So here there is a significant difference in the damping of isolation and damping of superstructure. So this particular case becomes the non-classical damping, right? And in non-classical damping, we have to use the superposition of the superstructure part and that of the substructure part. The next step is to do the eigenvalue analysis. Okay. Once we have mass and stiffness matrix, we can go for the eigenvalue analysis. And eigenvalue analysis are nothing but the frequencies and mode set. Here, the first mode frequency is coming 3.104 radian per second, and the second mode frequency is 25 point something radian per second. Now, when these are converted into time period, it gives 2.024 second, and the second mode period is 0.25, right? And in the next, we have mode shapes. Means the first, this represents the first mode shape and second column represents the second mode shape. Now it is very interesting to note that the isolation period, see, the fixed base period was 0.4 second. Fixed base period of single storied building under consideration was 0.4 second. And the isolation period of the base isolated building, TB, it was 2 seconds. Okay. So these mode shapes are for the base isolated building. It is not for the fixed base building. So we can see that the first mode period, 2.02 second, is very much close to the isolation period of 2 seconds. Okay. So this is the typical characteristic of base isolated building. You know, the first mode period is nearly equal to the isolation period. That means the isolation mode is the dominant mode, which we will see in the next slide. Okay, so in next figure, we have plotted the mode shapes and frequency. So we can see the first mode period is 2.02 second, which is close to this TB isolation period, and the second mode is something like this. Now there is many things to understand in the mode shape. It says so many things. First one, the displacement is mainly concentrated at the isolation level. We can see the relative difference of displacement between this fixity and the base mass. It is 1. Relatively, it is 1. Then the displacement of the first floor is 1.041 second. Okay. So the relative displacement is just 0.04. So we can say that the superstructure is nearly behaving like a rigid body with very small interstory drift. And the displacement is mainly concentrated at the isolation level. Therefore, the first mode is called isolation mode, in which there is very small displacement in superstructure. Okay, majority of the displacement will be at the isolation level itself. Therefore, it is called isolation mode. Isolation mode. Now, second mode, you can see in second mode, the relative displacement is more. Okay, it is equal to 1.641. So here we can notice the displacement in the superstructure, right? Therefore, this mode is called structural mode. Structural mode means first mode is isolation mode and the second mode is the structural mode. Okay. The contribution of structural mode is very less, that we will see in the next slide with some numerical value. So here we need to understand that there is no deformation or very small deformation in superstructure during first mode, and the deformation is mainly concentrated at the isolation level. So this is regarding the eigenvalue analysis and understanding of the mode shapes and frequency of base isolated building. Now, see, in order to have the complete analysis, we have calculated the generalized mass. Okay, we can use this formula, and generalized mass will be in two modes: M1 first mode generalized mass and the second mode generalized mass. They are coming like this. Okay, 1.75 and 1.07 times the mass. Then generalized damping can be calculated using this simple equation, right? So in first mode it is coming like this, and in second mode it is 2.737 times the mass. So these are the generalized damping value. Now the important thing is here modal damping ratio. Okay, the generalized mass are used to calculate the modal damping ratio, right? And modal damping ratio is essential in response spectrum analysis. We have used the same equation. See, C is equal to 2 times zeta into M into omega. So upon putting value of C1, M1 and omega 1, we have zeta 1 is equal to 9.64%. Means modal damping ratio in first mode, it is 9.64%, and the modal damping ratio in second mode is coming 5.05%. Now we know that in first mode, the displacement is concentrated at the isolation level. So we can see that the modal damping in first mode is very much close to the damping of the isolation system, which was 10%, right? So 10% and 9.64%, it is very close. This again shows that the first mode is the isolation mode. Okay, majority of the energy is dissipated through deformation of the isolation system. Okay. And the second modal damping ratio, in which we have structural deformation, and that is coming around 5.05%. So this modal damping ratio will further used to calculate the spectral acceleration in response spectrum analysis. Then modal participation factor. Okay, modal participation factor is for first mode is coming 0.976, and in the second mode it is coming 0.0238. Again, this number says that the first mode is the dominating mode compared to the second mode. Now, for the calculation of base shear and other response quantity, as you know, we use the IS code spectrum for response spectrum analysis, right? So T1 means first mode time period, that was 2.024 second, right? And the second mode time period, it was 0.25 second. Okay, these two time period we obtained by performing the eigenvalue analysis, which is shown in the previous slide. Now, corresponding to 2.024 time period, we have chosen this blue colored graph, because blue colored graph is drawn for 10% damping, right? And you know, in first mode, the damping is 9.64. Therefore, we have used the corresponding graph. In second mode, the modal damping ratio is 5%. So we will be using the red color graph for the second mode. Now, looking to this blue colored graph, the spectral acceleration at time equal to 2.024 second is 0.538 times gravitational acceleration, right? It is shown here. And for this, T2 is equal to 0.25, the spectral acceleration is 0.25 g. Okay, so these values will be utilized later. So we go to the next. In next, the modal displacement, they are calculated using this formula. See, IS 1893, their format can be slightly different, but the formula is the same. So the first mode displacement is coming like this, 96 millimeter and 100 millimeter. Okay. And in second mode, the displacement is coming 0.17 and minus 0.11 on the first floor. So looking to this value, we can finally prepare one table just after having calculated the equivalent nodal static force. The nodal static force are obtained using this formula. So F1 is coming this and F2 is coming this. F1 is the nodal force on degrees of freedom number 1, and F2 is the nodal force on degree of freedom number 2. DOF number 1 is taken at isolation level and number 2 is taken at the first floor level. So looking to this value, we can see that this 098, that becomes the base shear in first mode, and 0069 becomes the base shear in second mode, that is VB1 and this is VB2. So base shear in first mode VB1 is 0.098 W, and that in the second mode it is this 0.0069 W. So we can see significant amount of base shear is found in the first mode, and very small base shear is found in second mode. That again shows the dominance of the first mode. Okay, so the first mode is dominating so far as base shear is concerned, isolated displacement is concerned, nodal forces are concerned, etc. So let us have a summary of the responses calculated via response spectrum analysis. The first two columns, they shows the response of base isolated structure, and the last column shows the response of fixed base structure. Now the first mode base shear is coming 0.0099, and the second mode base shear is coming 0.007. And at last SRSS value is taken. So we can see that the SRSS value is nearly same as of the first mode base shear. Okay, so that shows the contribution of second mode is negligibly small. Okay, similarly, the isolated displacement in first mode is coming 96.4 millimeter, whereas in second mode it is very small compared to 0.17 millimeter. So SRSS value of the displacement is again same as that of the first mode. So there is no harm in omitting the second mode. Okay, dominating mode is the first mode. Now, the SRSS value of a base shear of a base isolated building is 0.099, and the base shear, normalized base shear of fixed base building is 0.63. So we can see for fixed base it is 0.63, and for base isolated it is around 0.1. Okay. So we can see there is a huge reduction in base shear is achieved because of the flexibility of isolation system. So the point to note is the first mode is the isolation mode, which is the governing mode, and the contribution of other mode is relatively small. They are usually negligibly small. Okay. So we have ascertained this thing with the example of single degree of freedom system. Now, another interesting feature of a base isolated building is this rigid superstructure assumption. See, while studying the eigenvalue analysis, that is mode shape, it was shown that during the isolation, during this displacement at isolation level, the superstructure behaves like a rigid body. So, the superstructure can be assumed as a rigid body. One example is given here. For TB, isolation period is equal to, let us say, 2 seconds, and damping is equal to 10%. Okay, same values are taken as previous. The pseudo acceleration for this system coming to be 0.54 times the gravitational acceleration. This is obtained from the IS 193 response spectra, and the isolator displacement UB is calculated by assuming the superstructure to be rigid. Okay. Simple equation is used. The acceleration A is equal to omega square into displacement. It's a well-known equation which we use in structural dynamics. So displacement D is equal to A upon omega square. You can see displacement UB is equal to A upon omega B square. So omega is expressed in terms of 2 pi upon TB. So after putting this value, we are getting UB is equal to 0.097 meter, right? So isolator displacement, see here I am writing two things. The superstructure is flexible, and superstructure is assumed as rigid. So when I assume superstructure rigid, I am getting isolator displacement UB is equal to 0.097, right? And the isolator displacement, by considering superstructure flexible, previously it was, right, 96.4 millimeter. So this is very close, 96.4 millimeter. Okay, so we can convert to them into 0.0964. Okay, so these two values are comparable. Okay, so if we assume rigid superstructure, then we have reasonably accurate values of the structural responses. So superstructure can be assumed rigid, but later we will see that upon increasing the superstructural flexibility, this relation doesn't hold true. That we will see in the next slide. Now, with this, we have completed the first part. Okay. The first part was regarding the concept and under which condition the base isolation is effective. Now we will move to the second part, that is effectiveness of base isolation system. We have seen that base isolation system is effective, but for certain cases it is not effective. Rather, in certain cases, it amplifies the response that we will see here. The first case is soft soil. See, we all know that the response spectra, the shape of response spectra obtained on hard soil, it is something like this. Initially, we have steep, then maximum, and then it reduces. Okay, so it's a typical shape of response spectra obtained on hard or medium soil. But if the response spectra is obtained on soft soil, then it has some different nature. It is something like this. Initially, it is low, and then it is increasing. It is something like this. A spectral acceleration by time period. Here, a typical response spectra obtained on soft soil is shown. So you can see initially the spectral acceleration is small, and at high value of time period, you will notice one hump. Okay, that there is increase in the spectral acceleration. So we take this same example over here. The fixed base building, fixed base time period is 0.4 second, and isolation period is equal to 2 second. So for 2 second, you will notice that the spectral acceleration is 0.63, right? And for fixed base building, the spectral acceleration is 0.24, 0.25 G. Okay, this is for fixed base and this is for base isolation. Okay, so you can notice that the scenario is completely reversed. Okay, here upon putting the system on isolation, the spectral acceleration increases. Okay, which further amplifies the structural response. Okay, so you can notice that there is a same building, same isolation system, but the soil is different. Okay, on a soft soil, it amplifies the response rather than reducing the response. So it seems a foolishness of using base isolation system on soft soil. Okay, just for our interest, one ratio is plotted here: 0.63 divided by 0.25. It is coming 2.52. Means when the building is kept on isolation system on soft soil, for this particular example, the response will be 2 times more than that of the fixed base system. So there is no advantage of using base isolation system at all. Okay. So soft soil is not suitable for seismic isolation. Uh, See, this is typical response spectra. This spectra is plotted for the 2015 Gorkha earthquake in Nepal. Okay, so you will see some strange response spectra. Initially, we have high value, and then it decreases. Then in moderate time period, it is relatively small, and then again, upon increasing the time period, a hump is observed. Means the spectral acceleration values are increases. So this type of earthquake is harmful for short period structure as well as long period structure. Okay. So it's a typical response spectra which was observed during this Nepal earthquake. Then the second point regarding the effectiveness, it is not effective for flexible superstructure, right? Because see, the time period, fixed base time period is suppose 2 seconds, and the base isolation period is also 2 seconds. Why the fixed base period is such large? Because the system is flexible. Okay. So when the flexible system is again kept on base isolation system, see, the flexible system is already flexible, and again it is made more flexible by keeping them on isolation system. Okay, so that will create user discomfort by increasing the lateral displacement and interstory drift, and we can notice a very small reduction in the structural response. So it is shown by these three graphs. Okay, the 2% damping graph, and then 10% damping graph, and finally 13% damping graph, because 13% damping, modal damping ratio in first mode is coming 13%. So flexible superstructure is also not suitable for base isolation system. So there are basically two candidates for which the isolation system is not useful. So these are the calculated responses for flexible superstructure, right? And here we can notice that the first mode and SRSS value is not nearly same. Okay, it is due to the flexibility. In rigid superstructure as assumption, the first mode was dominant, but now the dominance is reducing due to the flexibility. Okay, then the base shear of fixed base building is 0.70, and the base shear of base isolated building is 0.11. Okay, this is 0.15. V for fixed base and V for base isolation. See, here reduction is there, but it is not as high as that of the rigid building. Okay, in rigid building the reduction was around 87%, but here the reduction is relatively small. Okay, so the flexible buildings are not suitable for base isolation. Now, base isolation of multi-storied building, we will quickly go through this. We have one multi-storied building, 5-storied building. The fixed base period is 0.5 second and the isolation period is 2 seconds, and 2% superstructure damping is assumed. Both of the system are same. One is fixed base and the other is base isolated. And these are the eigenvalues. Okay. See, first let us examine the fixed base property. The first mode period is 0.5 second and these are all higher mode periods. And effective modal mass in first mode is 87.90. Isolated building, the first mode period is 2.041 second. Okay, again we can ensure that the first mode period is nearly equal to the isolation period of 2 seconds, and the effective modal mass in first mode is nearly 100%. Okay, so first mode is dominating mode and the contribution of higher modes are extremely small. Okay, in fact third, fourth, fifth and sixth mode, uh, the effective modal mass is nearly zero. Okay, whereas here we can see some amount of effective modal mass is there for higher mode. Okay, so this is regarding the dynamics of multi-storied building. Now, with this, our second part is over. Now, third part, dynamic analysis of base isolated building. See, the analysis is carried out first by writing the equilibrium equation, dynamic equation, and this is the general form of governing equation of motion of MDF system, where M is the mass matrix, C is the damping matrix, K is the stiffness matrix, R is called influence coefficient vector, x double dot g is the ground acceleration, and x double dot b is the acceleration of the base mass. For base isolated structure, usually two different equations are written. One equation is written for superstructure and the second equation is written for the base mass. This is due to reason that base mass directly resting on the isolators, right? And the isolators, you know, they are nonlinear. So in order to compute or in order to take into account the nonlinear behavior, the equation is written separately for the base mass and separate equation is written for the superstructure. So first equation is for superstructure and the second equation is written for the base mass. Okay, these two equations are combined together to solve it using any numerical time stepping methods. Now here FB is nothing but the non-linear bearing force or isolator force that is to be calculated by using the force deformation behavior of a corresponding isolation system. So here two type of isolation system along with their force deformation behavior and mathematical model is presented. One is lead rubber bearing or NZ system and the other is friction pendulum system. So the force deformation behavior of NZ type system is this. CB is damping, then KB is the stiffness, alpha is pre to post yield stiffness, FY is the yield stiffness, and Z is the hysteretic component. And in friction pendulum system, we have two components, that is stiffness and friction. So force due to stiffness component is KB into XB, and that due to the friction component, we have mu W into Z, where Z is non-linear component and it is obtained by many methods, right? And one simplest method is to use the Bachmann's well-known Bachmann hysteretic model, which is described by a single order differential equation, and one can use any numerical method like Runge-Kutta, fourth order Runge-Kutta or any other suitable method can be used to solve for Z hysteretic component. So once we get FB, that is substituted in the equation, and then further evaluation of response can be carried using Newmark method or central difference method or any other time stepping method can be used to carry out the analysis. Now here, in order to present the analysis result, a typical earthquake ground motion is used, and the earthquake ground motion is here is a synthetic earthquake ground motion. So this earthquake ground motion is obtained artificially so that its response spectra matches with the IS code response spectra. Because these artificially generated or spectrum compatible ground motions are used to perform final non-linear analysis of the base isolated structure to verify the design of the base isolation system that we will see in the next. So the artificial earthquake is used to perform the nonlinear analysis, and the results are presented. The results are presented for this artificial earthquake for FPS system, right? Three quantities are plotted. The top floor absolute acceleration, right? It's a multi-storied building. Here you can see 5-storied building isolated by friction pendulum system. The acceleration of top floor is shown. You will see two graphs, green color and red color. The peak value of green color, that is fixed base. Fixed base spectral acceleration, top floor acceleration is 2 times the gravitational acceleration. And the red color, it is for base isolated building. The top floor acceleration is 0.43. So we can see there is a significant reduction from 2.04 to 0.43. So the structural responses are reduced greatly when they are mounted on base isolation. The second graph, the second history represents the isolator displacement. Okay, so it shows how the isolator moves. Okay, so the peak value of isolator displacement is found 81 millimeter. And the last graph, it represents the variation of base shear. Okay, for fixed base building, the base shear is equal to 1.14 times the weight of the building, and that for base isolated building is 0.13 times the weight of the building. So you can see there is a dramatic reduction in base shear from 1.14 to 0.33. So here it can be said that base isolated building or base isolated structure reduces the structural response at the cost of allowing higher displacement at isolation level. Okay, one has to make suitable arrangement to allow the higher value of displacement of the order of 81.3 millimeter. Okay, whereas in fixed base building there is no such displacement. Okay. So this graph is very much useful to understand the effectiveness of base isolated building after performing the nonlinear time history analysis. It's a typical force deformation behavior of friction pendulum system. It is also known as hysteresis loop. You know, the area under hysteresis curve represents the amount of energy dissipated. So larger is the area, then larger is the energy dissipated during earthquake. Then seismic isolation technology can also be used for bridges. Okay, when it is used for bridge, the isolation bearings are provided between the deck and the pier. Okay. So we can see the isolation bearing is provided between the deck and pier. Of course, it is also provided between the deck and the abutment. Right. So the typical enlarged view of this region is shown here. Okay, this figure shows the actual example where we can see the friction type bearing is installed between the deck and the pier. The mathematical model for computational purpose can be shown like this. The pier is discretized into smaller elements, right? And the deck is also discretized. And finally, the time history analysis is performed to evaluate the response. And that response is plotted over here. And we can see there is a huge reduction in deck acceleration, pier base shear, right? For isolated and non-isolated. Blue color is for isolated structure, and we can see there is a reduction, significant reduction in the two response quantity. And the last history represents the bearing displacement. Okay, so this is the another example for FPS type system. Okay, previously this was for lead rubber bearing, and this example is for friction pendulum system, and we can examine the numerical values. For fixed base bridge, the deck acceleration is 0.32, and for base isolated it is 0.08. Okay. Pier base shear is also reducing drastically from 0.11 times the weight of the deck, it becomes 0.045. And here we can see the bearing displacement. The peak value of bearing displacement is found 54.7 millimeter. That is around 5.5 centimeter. It is under well-known Al Centro earthquake ground motion. Further, the seismic isolation can also be used for liquid storage tank. Okay. We all know that for performing the dynamic analysis, the liquid inside the tank can be divided into three parts, that is called sloshing or convective mass, then impulsive mass and rigid mass, when the flexibility of the tank wall is taken into account. Okay. If the tank wall are assumed rigid, then the liquid inside can be modeled by two components only, that is sloshing and impulsive, as we do as per our IS 1893. Okay. But when we take the flexibility of tank wall into account, it is modeled as a three component: sloshing, impulsive and rigid. Uh, See, this figure shows the actual implementation of base isolation technology for liquid storage tank. Okay. We can see small number of isolators are used. There is a circular tank which is under construction. It was under construction at some time in Greece. Further, to show the effectiveness of base isolation for liquid storage tank, the seismic response, the time variation of response of liquid storage tank with FPS under Imperial Valley earthquake ground motion is shown. Okay. So we can see the base shear of fixed base tank is 0.62, and that for base isolated tank is 0.25. Okay. So we can see the reduction in base shear. Then impulsive displacement is 2.25 for fixed base tank, right? And sorry, 2.25 is for base isolated tank, and 7.48 for fixed base tank. So further we can see the reduction. But it is interesting to note that convective displacement for isolated system is 2000 millimeter, and that for fixed base system is 1520. That means when the tanks, liquid storage tanks are kept on isolation system, its convective displacement increases, whereas base shear and impulsive displacement reduces drastically. Okay, so we can have proper trade-off for this, because the increase in convective displacement can be taken care of by providing more freeboard. Okay. But the reduction in base shear and impulsive displacement is very much beneficial in reducing these structural quantities. Okay, because the response is reduced, and therefore we can have lighter design. There is a slight increase in convective displacement, that is true, but that is taken care of by providing slightly more freeboard, free surface above the liquid, right? So this is how the base isolation is effective for liquid storage tank as well. Then this is regarding seismic isolation for near fault earthquake. See here, two earthquake ground motions are shown. One is near fault earthquake. On the left side, it is near fault earthquake, and on the right side, it is far field earthquake. Okay. The top figure represents the acceleration history, right? And the bottom figure, it represents the velocity. The velocity time history is obtained by performing the numerical integration of acceleration time history. So looking to the velocity time history of near fault ground motion, we can see a distinct pulse, high velocity pulse of long duration is observed in the velocity history of near fault ground motion, whereas no such high velocity long duration pulse is observed in velocity history of a far field earthquake. So this is the main difference between the near fault earthquake and far field earthquake, right? It is called far field and this is called near fault. So what is the consequence of this high velocity long duration pulse? See, the duration of this pulse is in the range of 1 to 3 seconds, right? And we know that the isolation period is usually taken between 2 to 4 seconds, right? So isolation period 2 to 4 seconds, and the duration of this pulse is also in the same range. So what happens? Resonance condition resonance take place. So base isolated buildings are more prone to create resonance condition under near fault ground motion. So performance of base isolation system under near fault ground motion is not satisfactory. Right? So this is the point which we should keep in our mind. Same thing is mentioned over here. So these pulses will have a large impact on isolation system with a period in this range and can lead to a large isolator displacement. So we need large size of isolation system. In order to take care of this problem in developing country, they are using the concept of transfer trusses. Okay. So here one figure is shown. This is superstructure, and this is isolation, and in between transfer truss girders are used. The role of transfer truss girder is to reduce the number of bearings. Okay. Usually one bearing is provided below column. So looking to the configuration of this structure, around 24 isolation bearings are required. Okay. And by using this transfer truss, it has been isolator to accommodate large isolation displacement resulting from near fault ground motion. So this concept is used in Japan. This concept has been used in large building Japan to take care of large displacement demand of the isolation system. Then base isolated building with SSI. Okay, we will quickly cover this part. See, when the soil structure interaction or the flexibility of soil is taken into account, one point one should understand, it is this. When the flexibility of isolator and soil are close to each other, then the SSI may be significant. Means the flexibility of isolation and the flexibility of soil both are comparable, both are in the same range, then the influence of soil structure interaction will be significant. Otherwise, there is little influence of SSI on base isolated building. Okay, so this is a single point which we need to consider with respect to the base isolation system. Then this is regarding the testing requirement. Okay, as per IBC 2000 code, that requires at least two full-size specimen of each type are to be tested under two combination, means vertical load and horizontal load, right? So there is a special testing ring testing setup, and it is horizontal actuator which provides the horizontal displacement, and the isolation system, isolation bearing is here, which is under axial force. And then by performing test, the force versus deformation relationship hysteresis loop is obtained. So we have finished the third part, and now we are moving towards the last part, design of base isolated building. So design of base isolated building, there are three main steps: the design of isolator, and second step, design of base isolated building, that is superstructure, second part, and the third part is checking part. Okay. In first part, the isolation system is designed. In second part, superstructure along with isolation system is designed, and the third part is checking by nonlinear time history analysis. So let us see all the steps quickly. See, the first point, design of isolator, means the first step of isolated building design, design of isolator. See, the objective of the design of isolator is to obtain the effective stiffness, K effective, and damping, zeta effective of the isolation system. And for that, the three criteria are used. These three criteria are very important. The first criteria means, see, what is the base, what is the basis of designing the isolation bearing? Okay, there can be three bases. Number one, good separation of time period between the fixed base structure and base isolated structure. Okay. Usually, the separation is taken around 3 to 4 times the fixed base structure, right? That we will see later in the example. Then second criteria is specified maximum displacement of the isolator. Means maximum isolator displacement is restricted and accordingly the system is designed. Okay. And the third criteria is specified maximum spectral acceleration. Here the spectral acceleration is restricted and accordingly the other parameters are designed. Okay. So these are the three bases on which the isolation system is designed, and we will see one by one. First, good separation of time period between the fixed base structure and base isolated structure. See, as per this criteria, the TB means time period of the base isolated building is taken as 3 to 4 times the time period of the fixed base system. Okay. So, for example, if we take 3 and if the time period of fixed base system is 1, then the base isolation period according to this formula would be 0.3. Okay. However, UBC says that in no case the isolation period is kept less than 2 seconds. Okay. So normally the isolation period is taken as 3 to 4 times the period of the fixed base building. Right. So this graph can be used, and when the time period increases, the spectral acceleration and base shear is reduces, as we have discussed earlier. Now, second criteria, the specified maximum displacement of the isolator. See, as per the second criteria, the maximum displacement called design displacement is specified. Okay. So here we can see the design displacement is, let us say, 0.2 meter. Okay. So this is specified. Means in no case the isolator displacement exceeds the 0.2 meter. Right. So if this is specified, we can read the value of time period. Okay. And from the value of time period, we can further go to the value of spectral acceleration. Right. So that is shown here. Once you know the spectral displacement, we can easily read the value of spectral acceleration. So as per the first criteria, SD, spectral displacement, is specified, and from spectral displacement, isolation period and spectral acceleration are calculated. Okay. So this is the most common type of criteria used for the isolation system design. And the last criteria, where spectral acceleration is specified. So we can have look to this figure. See, the spectral acceleration is fixed, right? And then from spectral acceleration, we can read the time period, and then we can read the spectral displacement. Okay. So third criteria is particularly useful for the design of secondary system. Okay. When the building holds some sensitive equipments and some sensitive machinery, for the design of isolation system of this machinery, the third criteria is usually used. Okay. Because acceleration control may be required for human comfort as well. So, like this is specified. Then we go down to get the time period, and from time period we calculate the spectral acceleration. So here, what is the sequence? SA is fixed, spectral acceleration is fixed, and from SA, TB and SD are calculated. Okay. In second criteria, SD was fixed, and from SD, TB and spectral acceleration was calculated. And in the first criteria, we decided TB, time period of base isolation system, equal to 3 to 4 times the fixed base period. So from TB, we calculate SA and SD. So this is the difference between the three criteria of design. Right. Now here the design of base isolated building is mentioned. It's again a three-step process. First is preliminary design. Okay. In preliminary design, the superstructure is assumed rigid. Okay. So this is superstructure kept on base isolation, base mass, and here is the isolation bearing. The superstructure is assumed rigid, and some base shear is calculated using formula like Z by 2 I by R SA by G into spectral acceleration. Base shear is calculated. Now, this base shear is equally distributed at all floors. Suppose our example is of 3-storied building, then it is distributed equally on all the floors, right? And then the normal analysis is carried out under various load, dead load, live load, etc. So this is called preliminary design, right? After doing preliminary design, the response spectrum analysis is carried out. Okay. That is discussed in the next slide. After preliminary design, the superstructure is analyzed under response spectrum loading. And while performing the response spectrum analysis, the building is modeled like this. Suppose these are the different floors, then it is kept on rollers, and a horizontal flexibility of isolator is modeled by providing spring of equivalent stiffness. Okay. So see, for example, suppose we had two isolators, and the isolation stiffness is suppose Kb. So what should be the stiffness of these springs? It is equal to 2 times Kb, because we have two isolator. Number of isolator multiplied by the stiffness of each isolator. So we provide a horizontal spring, and the building rests on the roller, and then the analysis and design is carried out for different load combination, dead load, live load, response spectrum loading, as we do normally. Okay. So we got the final sizes, right? So with the second step, our majority of the design work is over. In third step, the designed structure is checked by performing the nonlinear time history analysis. So whatever design we got in the second step, it is checked by performing nonlinear time history analysis, in which the isolation system is modeled by considering its nonlinear effect. And if the results are between the nonlinear time history analysis and response spectrum analysis are close, then the design is okay. Otherwise, the iterative process is carried out till the two results are comparable. Okay. So in this way, the design process is carried out. So this is the third step, checking of design by nonlinear time history analysis. So one simple example is given here. It's a 10% damping is considered. It's a 5-storied building, and the column load for one particular bearing under dead load, live load condition has been found 800 kilonewton. For 800 kilonewton axial load, the bearing is designed. So we will go quickly because we are falling short of time. So, bearing is designed in 2 steps. Okay, first isolator properties are calculated, and in second step, the geometric design of the isolation system is carried out. Geometric design means the diameter, the height, the thickness of several layers, different layers are computed. They are called geometric design. Isolator properties can be effective stiffness, design displacement, characteristic strength. They are all shown in this figure. It's a force deformation behavior of bilinear isolation system like NZ system. Why it is called bilinear? Because it has two slopes. This is primary slope, primary stiffness, and this is secondary stiffness. The primary stiffness is shown by K1 and the secondary stiffness is shown by K2. The peak displacement is called Dmax. It is design displacement. Basically, it is the design displacement. And Q is the characteristic strength, and Fy is the yield strength of the system. Normally, this is shown by ratio like alpha times K1. Okay, alpha is called pre to post yield stiffness ratio. So these properties are calculated, and see, basically there are formulas. These formulas are derived using simple structural dynamics, right? Ka is equal to something like pi square upon Tb square. R is the radius. See, that equation is here. You know, T is equal to 2 pi root R upon G. That sort of equation can be used. This equation is used to calculate the design displacement. It is nothing but, see, zone factor multiplied by spectral acceleration divided by omega, and beta is damping modification factor, and I is the importance factor. So using this formula, we can have the isolator properties, and this figure shows the designed isolation bearing, means its diameter is coming after performing the calculation as 500 mm, thickness is 500 mm, then thickness of rubber layer, thickness of steel plate, diameter of the lead core, etc. can be calculated using the equations presented earlier. So this is how the bearing is designed, and we see how the superstructure is designed. Okay. Then at last, we have quick overview of base isolation across the globe. Means, see, this figure shows the isolation used for bearing, buildings. It's a low-rise building where isolation is used. Second figure shows the application of base isolation in bridge, where we can see isolation bearing is provided between deck and the pier. Then in third figure, it shows the application of base isolation for LNG storage tank, huge liquefying natural gas. They can be used. In next figure shows a typical base isolated demonstration building constructed in Indonesia. Uh, the high damping rubber bearing is used here, and one interesting thing to see is we can see all services, right, and the services are connected to this chamber, and this connection must be flexible connection. Okay, these flexible connections are usually very costly. Then another application that shows the uh, under construction view of nuclear power plant, right? So base isolation is also used for nuclear power plant, which we can see further in this figure as well. Then base isolation is also used for protecting the sensitive equipments. So in this figure, we can see one typical floor, and these are the sensitive equipments, and these sensitive equipments are placed on isolation bearing, right? Bearings are provided on one particular floor on which the equipments are mounted. So isolation can also be used for protecting the secondary equipments. And the last example that shows that isolation is also used for retrofitting of structure. These are all newly constructed facility, but base isolation can also be used as one of the retrofitting option. This is the example of San Francisco City Hall. This was constructed in 1915, and the fixed base time period was 0.9 seconds. Right. Then it sustained the substantial damage from Loma Prieta earthquake, and it was found to have necessary repairs and strengthening after the earthquake. Now, in order to preserve the historic fabric of the building, base isolation was adapted for improving the seismic resistance in terms of retrofitting option. And the superstructure, it was strengthened by providing new shear wall inside the building so that the outer fabric of the building can be conserved. And later, 530 lead rubber bearings were inserted, and after that after that the period was found to be 2.5 seconds. Initially it was 0.9 second. After retrofitting, it becomes 2.5 second, and the retrofit project was carried out in 1998. So this is the good example of base isolation used as a retrofitting option. Then here the cost effectiveness of base isolation system is shown. Like, say, the different elements are shown: foundation, structural element, isolation layer, non-structural element, then cost of elevator, and total building cost. So one thing to note in this component, foundation component, see, conventional SMRF means fixed base building, and this is isolated building. So we can see the increase in cost for base isolated building for foundation component. See, the percentage increase is shown here. 34% cost is increased. But this increase in cost is compensated by lighter design of the superstructure. Structural elements, we can see 30% reduction is observed in the design of superstructure. Okay. Note that this study, actually this one study was carried out on a 3-storied building of this dimension, and the rates are given in 2008 market rates in US. isolation layer, it is costing like this, around this. And finally, we can see the gross increase in cost is around 10% if we go for seismic base isolation. This shows the cost effectiveness of base isolation. Now, a question may come to our mind that what is the scenario of isolation in India? We know two buildings are there in India. One is well-known Bhuj Hospital, right? And here the isolation bearing is provided. Lead rubber bearing is there. And the another example is base isolated showcase building at Noida. See here, this yellow colored portion shows the bearing, isolation bearing, and the enlarged view is shown here. A double friction pendulum bearing is used. It has two surface sliding, top and bottom surface. And this is another closed view of isolation system. So we can see very few building, base isolated building in our country. Then again, a question may come to our mind that why people are reluctant towards base isolation in India. So I have tried to summarize the reason. The number one is lack of awareness of the benefits of base isolation among owners and real estate development. This could be one of the reason, right? The another reason is unavailability of design guidelines of the base isolated structure. So as such, no design guidelines are available in our country. And the third reason could be lack of skilled and experienced civil contractors dealing with base isolated structure. So because of this reason, the building stakeholders are more reluctant in adopting the base isolation technology in India. So these are the few reasons for that. In a summary, the most suitable candidate for seismic base isolations are steep structure, means flexible structures are not suitable. Steep structure rested on hard soil, such as low rise and medium rise building, nuclear power plants, bridges, large liquid storage tank, and many types of equipment. They are the most suitable candidate for base isolation. High-rise buildings are not suitable. High-rise buildings are not suitable for base isolation due to its high fundamental period. For building rested on very soft soil, base isolation is not suitable as it shifts the structural fundamental period into more critical range. Lastly, in general, only certain type of structure are presently suited for base isolation, although technology is gradually overcoming these limitations. So this is the summary of the presentation. These are the important references which I have used to prepare this presentation. With this, we end our today's discussion. Thanks for your patience hearing.
Thank you very much, sir, for making our last session of the 5 days faculty development program more useful and more informative. This would be certainly have benefited all the participants in enhancing their knowledge. You make us clear with various important topics like the concept of base isolation, conditions in which isolation is effective in reducing the seismic forces, rolling bearing system, analysis and design of base isolated structures, and many more. Sir, can we open up for questions if you permit?
Yes, please.
If you have any query regarding this session, you can please ask. Please raise your hand if you have any query.
Yeah, participant can raise your hand. Yes, Rachana, Dvojas.
Am I audible, sir?
Yes, yes, audible.
Sir, actually, I want to do the PhD in related to this base isolation, but as it is not possible to do the practical sessions, then which softwares are useful to this base isolation?
I think you please drop an email and we will further discuss.
Okay, sir, okay. So your mail ID?
Yeah.
Yeah. By the time Ronak Motiani, please.
Thank you, sir. Very good afternoon, Sony sir.
Good
I have one
afternoon.
question. I have one question about the response spectra that you showed for the soft soil and medium soil. So, sir, is it necessary to have a site-specific response spectra when we are going for this? Because recently I have seen one or two articles saying that the response spectra for the soft soil and medium soil for the Gujarat region is not matching the IS spectra. They have a quite significant difference.
Yes, it is very much mentioned in our new IS 1893-2016 that for important building, site-specific response spectra should be developed. And they have also made one condition that if the response obtained from site-specific spectra is less than that obtained from code-based spectra, then we should go for the
Conservative
code.
one should be taken. Conservative one should be adopted.
Yeah. So that is very much essential.
Okay, so thank you.
Yes, anyone else, please? Yogesh Chavan, please. Mr. Yogesh Chavan.
So under certain frequencies of the ground motion, the building might rock. What actions are taken for buildings isolated under such rocking effect?
See, while designing the isolation system, the rocking component is also taken into account. So one has to take precautionary measures at the design stage as well.
And so what height we can use, for what height we can use such isolators?
There is no fixed limit on height, but as we have discussed in the presentation, that it is suitable for low-rise building with relatively short period.
So is there any height to width ratio like that we can apply this system
No,
for?
there is no specific height to width ratio. That all depends upon the time period. Okay, the response is governed by the time period.
And are these bearings same as the bridge bearings, or is there any difference in this?
There is no, there is no demarcation in bearing that this particular bearing is for bridge and this particular is for building. There is no such demarcation. Any bearing can be used for any type of structure.
Because in bridges we are providing restrainers for which limits the movement of the superstructure. So
Yeah, but see, in old bridge you will find friction pendulum bearing, engine system, rubber bearing, right?
yes, they are provided, but along with that we have restrainers, uh, uh, side restrainers which restrain the maximum movement.
Yes.
So
They are usually provided to prevent the pounding effect, pounding between the deck. Some energy dissipation devices like dampers are also provided in between.
sir, you mentioned that they have been used for nuclear power plants.
Yes.
For what purpose they are used there?
Uh, the purpose objective is the same, to reduce the structural response. Okay, in NPP building, nuclear power plant building, see, many NPP buildings are isolated in Western countries. And the main purpose is to reduce the response.
What type of And sir, how the parking facilities are provided when these base isolators are installed in buildings?
The parking facility, again, that depends upon the geometric design planning stage. Here, see, for example, see in this building, right, you can see the basement. In fact, here you can see the basement, which can be used for parking purpose. It has nothing to do with the structural design of isolation system or superstructure design. Okay, that depends upon the functional requirement and functional planning.
Sir, in one of the slides, you mentioned that the building becomes more robust against earthquake.
Yes.
Uh,
Not all buildings.
Actually, we are installing the isolators to make the building compliant, but which is at the cost of adding a, fail- a weak weak zone, which might be the reason for failure of building.
Say, I cannot get your question.
Sir, we are adding isolators at the base, so it forms a weak zone where the failure may occur of the building.
Yeah. See, in the design, while the design of a base isolated structure, a gap is left on along the periphery of the building, that is called moat. Moat is to be provided.
Yes.